We'll study the repair problem in erasure-coded storage. Erasure coding has been widely deployed. Many enterprise systems reportedly use erasure coding to provide storage efficient fault tolerance. The most popular erasure code used today is resolvement codes. So the idea is you have two parameters, n and k, where n is larger than k. So we encode k original uncoded data blocks into n coded blocks, which is called a stripe, and such that any k of n blocks can recover all the data while maintaining the minimum redundancy n over k. So we call this property maximum distance separable MDS property. So if you look at the number of block failures that you can tolerate, let's say we take 1410 resolvement code. This is the parameter used by Facebook data centers. You can have redundancy only 1.4 times. While if you use replication, you need to make 5 copies to tolerate any 4 failures, so that will be 5 times redundancy. However, there's a drawback for using erasure coding is the high repair penalty. Essentially, when you repair every single block, you need to transfer multiple blocks. So for the case of resolvement codes, you need to transfer k blocks. So that means that you will have amplification in both bandwidth and I/O. The repair problem in erasure coding has been studied for a long time. And so but they all make different design trade-offs. So one state-of-the-art erasure code is called clay codes. This is the regenerating codes. So the idea is you can actually minimize the amount of data being read when you do a single block repair. And it, at the same time, achieves the MDS property. So this is implemented in Ceph, and we believe that this is the state-of-the-art regenerating codes. But the problem is constrained by the theoretical property, which is exponential subpacketization. Subpacketization means that you need to divide a block into multiple subblocks, and clay codes try to access the minimum subset of these subblocks. But that would imply that you need to make multiple non-contiguous accesses to these subblocks. So, and it's exponential. So we call them the seed, and so when you actually do the repair, the performance may not be that good, even though theoretically this is optimal. There are also some reputable erasure codes like locally repairable codes. Basically, you can repair a block using a subset of blocks. But the thing is, it is not MDS, so it introduces higher redundancy than resolvement codes. And also some papers talked about introducing MDS codes with small subpacketization. So they can reduce both the repair I/O and also I/O6, but there are certain constraints in their code constructions. So here, what we want to do is we want to achieve I/O efficient repair. We argue that I/O efficiency is much more critical than bandwidth efficiency, especially in high-speed networks that we found in practical data centers. So our goal is to design a new family of erasure codes that can preserve the RS code properties, including MDS, systematic, which means that the original data blocks are still there after you do the encoding. And also it can support general parameters n and k. And we want to achieve our efficient repair. So we not only want to reduce the repair I/O, the amount of data read, but also we want to reduce the I/O6, the number of non-contiguous accesses. And we want to apply the reductions same for the data and also parity blocks. Here we mainly focus on single block repair because single block failure dominates in practice, but we also want to address multi-block repair efficiency because recently people also propose wide stripes, and when you increase the size of a stripe, multiple block failures become common, so we also want to address that. So here comes our contribution. We call this LESS, which stands for Layering Extended Substripes. It's built on RS codes, and it can address the efficiency in single block repair and some cases of multi-block repairs based on this extended substrate idea. And also it allows small, but most importantly, configurable subpacketization. So you can control the number of subblocks that you want to use. And it's implemented on Hadoop HDFS, and it can achieve savings in both single block repair and also full node recovery times compared with clay codes. So let me try to summarize the whole work in one single slide. So the idea is you have three parameters now, N, K, and also alpha. Alpha is the subpacketization, the number of subblocks per block. So the idea is to construct an extended stripe N prime, K prime, where N prime and K prime will be larger than NK given by this formula. So for example, NK alpha, if you set this to 642, we will have N prime, K prime equals to 8 and 6. Now notice that here I assume that N is divisible by alpha plus 1, but in our paper we address the case when N is not divisible by alpha plus 1. So we can actually address any alpha between 2 and N minus K. So the idea is we layer multiple N prime, K prime extended substripe on a regular NK stripe. So when you want to repair a block in an NK stripe, it will be translated to the problem of repairing alpha subblocks in an N prime, K prime stripe. So for example, in NK alpha 642, traditional erasure codes will need to read K blocks to repair a block. So K is equal to 4. Now with less, you can retrieve K prime equal to 6 subblocks. And each block has 2 subblocks here. So 6 subblocks means 3 blocks. That will be 25% less than traditional erasure codes. The idea behind is based on a parity check equation. So we have this parity check matrix multiplied by these data blocks and also parity blocks that will be equal to 0. Now, this is usually used by coding theory community. Now, in system community, we usually do this in generator matrix form. So we take the data blocks, we multiply the generator matrix with that, and we will generate the parity plots, but they are actually equivalent. So the idea of parity check matrix is any N minus K columns here will be linearly independent. Then in this case, you can ensure the MDS property. So in last here, what we do is first we will divide these blocks into different groups, and then we try to organize the subblocks into alpha plus 1 extended substripes, and then we ensure that each extended substripe will be MDS based on Vandermonde-based RS codes. So let's go back to our example 642. So in this case, we have alpha plus 1, 3 extended substripes here. And we try to construct these substripes based on Solomon codes and ensure that for each extended substripe, any N minus K subblock failures are tolerable. So the encoding here is basically follow what we just saw in traditional Solomon code. So the idea is you have the corresponding parity check matrix, and then you just convert this into a generator matrix. You multiply the generator matrix with the subblocks, then you will have the corresponding parity subblocks. Now, if you notice in here, you will find that, hey, so how do you ensure that all these extended substripes satisfy the RS code properties? Because X3 actually is depending on X1 and X2. So you form X1 and then you form X2, but X3 depends on them. So how do you actually form 3 of them together? Now, in fact, when we do this last encoding, we don't need to encode all of them. We only encode alpha of them. So in this case, we only need to encode X1 and X2, and X3 will automatically become a Solomon code. So in this particular example, basically, after we form the parity check equations for X1 and X2, X3 basically is just the sum of the parity check equation of X1 and X2 and automatically satisfy the parity check equation in Vandermonde-based form. Now, to be more rigorous, actually, what we do is you encode alpha extended substripes by choosing carefully designed coefficients, and the last extended substripe will be automatically formed. So the details will be in the paper. Now let's take a look at some of the properties in less. So first of all is single block repair. We argue that this is efficient. Essentially, you only need to retrieve the subblocks within a single extended substrate. in general, for every block, we can ensure that there will be one extended subscribe that applies to this. So we can reduce the repair I/O. And also, we will keep small alpha and contiguous subblocks access. So you may need to access multiple subblocks in one block, but the thing is that will be all together. So we ensure that there'll be one single seek per block, one contiguous access to multiple subblocks. So then in this case, we ensure that we can limit the seek overhead. So as I said, every block will belong to one extended subscribe. So in this case, you can use the corresponding extended subscribe to repair the corresponding block. And we also make sure that the similar reductions for repair I/O and RCs will be applied to both the data and priority blocks. For multi-block repair, actually, the idea is as long as these multiple block failures are both in the same extended subscribes, then we can apply the same recovery for this particular extended subscribe to recover multiple subplots together. Now, it's not all the possible combinations, but for some combinations. So in our evaluation, there will be about 30% of cases that fall into this category. So for 30% of cases that we can also improve the performance for this multiple block repair. So it also preserves the RS code properties, meaning that it's MDS. So given that the coding coefficients are carefully chosen. So there will be a lot of theoretical proofs. You can find them in the paper. And it's systematic, and also it applies to general NK. So usually you can use Galois field 2 to the 8 or 2 to the 16 to support the commonly used coding parameters. Again, in the paper, we provide examples of what these parameters are. And for alpha, that will be between 2 and n-k. So we implemented this on top of Hadoop. It's based on one of our prior work, OpenEC. And we evaluate less based on numerical analysis just to count the number of IOs and RCs that we can reduce. And also, we conduct test experiments on a local cluster. So I highlight some results here for numerical analysis. So basic idea is less can repair the repair IO and also the IO seek. So the trade-off is when you increase alpha, you can reduce the amount of data being read. So that means you can reduce repair IO. The drawback is you have more IO seek. Now remember, one seek per block. So more IO seek means that you need to access more nodes to recover the data. So that's the trade-off we make in here. Compared to state-of-the-art, we can reduce the repair IO by this amount of percentage, and also compared to clay codes, which has exponential subpacketization, we can reduce this number of IOCs by a significant margin. We also did the testbed experiments on our local testbed. It's based on hard disk. And again, we measured the single block repair time. So x-axis means different schemes. Y-axis means the repair time, lower is better. And then we see that actually less, which is in yellow colors, we did better than the others. So for less with alpha equals to 4, then we can also reduce the time by this amount. During the artifact evaluation, we have a chance to access Shandong Cloud. So actually, even though the hardware specifications is different, we still achieve consistent performance improvement. Now, the absolute numbers are not the same. Actually, Shandong Cloud has better CPU and network resources than ours. So we see better throughput and also better repair performance. But the trend is actually similar. So our observations still hold. So to conclude, LESS is a family of repair IO efficient erasure codes aiming for reducing both the amount of data read and also IO seeks. And it's open source, so please feel free to verify. So I'm happy to take questions and comments.
Thank you.